Hello, today I'd like to talk about motion on an inclined track, Unit 3. My name is Phạm Việt Dũng from KK66. My student code is 66511130003. Alright, first one, let's look at the textbook. So, on the textbook, investigation of linear motion. The first part in the textbook, they introduce the apparatus. The second part is the procedure. The third part is collecting data. The fourth part is processing the data, and the last part, the fifth part, is conclusion from the experiment. Alright, so I will do as follow. About the objectives, knowledge and concepts. Objectives, students to conclude that the motion of the ball on an inclined track is not uniform, and they are to conclude that the average velocity increases uniformly. About skills, I would like to introduce a way to investigate linear motion, and the students can practice this way of investigation. They can design, they know how to design the experiment, they know how to observe and measure variables, they know how to record observation and measurement data, they know how to record data, and they actually record data successfully. They know how to process collected data and process data successfully as well. And is the experiment to investigate or verify concepts? What is the rationale? The experiment is to investigate linear motion on an inclined track. And we know that motion on horizontal air track is uniform, but we're not sure about the motion on an inclined track, so that's the reason why we need to do an experiment to investigate it. What will I do to make sure the lesson is eyes on? I will actually ask quite a lot of questions. The question I will ask is, I will ask students to design the experiment. I will ask them about the apparatus and how to use them in this experiment, and how they should put the photo gates in order to record time and distance in the best way. Alright, key phases. Phase 1, elicit the problem. This is what I do after reviewing the previous lesson, which is about uniform motion. I asked the students whether motion on an inclined track uniform, and I let them guess. So this is what students are expected to do. They will be expected to design the experiment. They have to express the functions of the apparatus and how to make use of them. They will actually do the experiment. They will record data and they will process data. They will draw graphs and compare with uniform motion and make a conclusion. About teacher's activity, I will ask them to know what motion on an inclined track is uniform or not, and I give them the problem. It's like we do an experiment to investigate the motion on an inclined track, so we need to design an experiment, and how can we design it? I asked them about the quantities that should be measured, how to measure the quantities and measure them by which devices. This is asking about the apparatus, and I will ask them to record the data on a table. So this is the student's activity. The students will have to design an experiment to check whether s, which is the distance, is a first degree function of time or not. And we create motion by using electromagnets and an inclined track with inclined angle about 5 to 10 degree. And the mission is to check the relationship between S and T so that the quantities need being measured are the distance and the time interval. The components of the experiment setup. The experiment setup using linear track and electronic timer or digital timer. Alright, the activity of the student continued. They will have to tabulate a table of expected data, and they will actually carry out and record data in the table, working in groups, recognizing that the graphs of S and T is not a straight line, and then they can conclude that the motion investigated is not uniform. I will ask them to give conclusions about motion on an inclined track after the experiment, and students are expected to do from the results obtained by the experiment. So they have to conclude that the motion on an inclined track is not uniform, and conclude that the average velocity increases uniformly. Alright, so that is my plan of teaching this experiment, and now we get to the actual experiment that I did. Okay, now let's move on to the experiment to investigate the motion of a ball, a steel ball here, as you can see, down an inclined track. And what we have here is an electromagnet which is connected to a button. When I hit this button, the electromagnet is switched off, and it will release the steel ball. And this electromagnet is connected to socket C. We have two photogates. Photogate 1 is connected to socket A, and photogate 2 is connected to socket B. And I set the mode is the mode is from A to B, which means it measures the time from when photogate 1 is started to be blocked, and to when photogate 2 is started to be blocked. And basically it measures the time the ball travels from photogate A, the position of photogate A, to position of photogate B. And along the track we have a ruler which measures the length between two photogates. So we read the length, which is the distance which the ball moves during the time it reads here. So what we will do is we will release the ball with the same inclination every time. We release the ball, and we actually move photogate B along the track with a specific distance. So we will do 10, 20, 50, 40, 30 and 60 centimeters. So first what we will do is we set the ball to the electromagnet. We set everything, set the timer to 0, and then we set photogate 2 to 10 centimeters apart from photogate 1. So this is 10 centimeters. And after that, we release the ball. Okay. Alright, so 10 centimeters will have 0.496 seconds, and we will move the photogate 2 to distance 20 centimeters. Right? And then we reset everything. Then we hit the button. Oh, sorry. I haven't put the ball back. Alright? And we reset everything to 0. We hit the button. The time now changes to 0.710 seconds. We do it again. And put back the ball. We move everything to 30 centimeters. So the distance now is 30 centimeters. Note that because photogate 1 is right in front of the ball, so the initial velocity is 0. And then we reset everything, right? And we hit the button. The time now changed to 0.8881 seconds. We do it again. We move this one to 40. The distance is now 40. We hit the button. The time now is 1.025 seconds. We do it again. We have 2 more values. Right? We move it to, this is 50 centimeters. Alright. Reset. Click the button. 1.153 seconds. Alright. So the last value, move it to 60. Right. Reset everything. Hit the button again. Alright. We have the time now is 1.270 seconds. And now we will process the data based on the data we received from the experiment.
And now we move to the table of data, and we will process the data as well. And in this table, as you can see, on the left column is the time recorded, on the right column is the distance. So when the distance is 0, we can actually say that the time is 0. So no doubt about that. And this is in centimeter. This is in seconds. Alright. And we will draw a graph about this. So distance and time. As you can see, the graph of distance versus time is not linear. It is actually a curve. So from this curve, we can conclude that the motion of the ball on an inclined track is not a uniform motion, because we have already known that in uniform motions the distance moved, the distance traveled must be a linear function of time, so it must be a straight line. But in this case, it is not. It is actually a curve, and it looks a little bit like a parabol. We don't know about that. We can actually check it, but we actually don't know. So this is the first graph. We can do a little bit more. We can actually calculate the average velocity by checking the distance and divided by the time. Right, and we will do it for every distance, and we can actually guess that when the distance is 0, the velocity is 0, because we released the ball from rest, so we can guess that the velocity is 0, because we cannot divide 0 by 0 to get the average velocity here. And I will actually do this. I will copy this right here, and we will do another graph. So we can actually see that the graph of the average velocity versus time is a straight line. So from this graph we can conclude that the average velocity increases uniformly with time. So once again, because the average velocity is not the same throughout the whole experiment, we can say that this motion, the motion of the ball on the inclined track, is not uniform, because we have already known that in uniform motions the average velocity must remain the same in every distance. All right, so those are two most important conclusions in this experiment. And if the students think that the distance is a second degree function of time, we can actually check it by doing this. So this is t squared time square, and we will take the square of the time here. We will take the square of the time. So t square here is the square of t here, and we can actually draw a graph of this. So from this graph we can see that it is actually a straight line. So S is definitely proportional to t square, and from this graph again we can conclude, again we can certify that motion of the ball on an inclined track is not uniform. So that is what the students are expected to do. And the last graph is actually optional. The two compulsory graphs are distance versus time, and average velocity versus time, and they are expected to record the data like this. They are expected to calculate the average velocity from distance and time, and after that they are expected to draw a graph of distance and time, and then draw a graph of average velocity and time, and then they have to conclude that they are expected to conclude that this motion is not uniform, and velocity is not a constant, just as in the textbook, as you can see here. Conclusion, general conclusion. Throughout the experiment, we can see that we can see that here from here. All right. This is just exactly like what we just have done. Yeah, as you can see, the average velocity of the car increases, so the motion of the object is faster and faster. So that is my whole teaching of this unit, and thank you very much for listening.